Shall I start?
Yeah, you can start.
Okay, thank you. Good evening, everyone. Welcome to the Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IASC. It's my pleasure to introduce today's speaker, Professor Harish Prasad Guruswamy. He will be speaking on layers as lenses, a narrative of feature learning in deep networks. Professor Harish is currently an assistant professor in the Data Science and Artificial Intelligence Department of IIT Madras. His primary areas of interest include machine learning, statistical learning theory, and optimization. He was previously a research scientist at the IBM Research Labs and a postdoctoral researcher at University of Michigan. He completed his PhD in Computer Science and Automation Department at the Indian Institute of Science, Bangalore, under the guidance of Professor Shivani Agarwal. Earlier, he pursued his master's degree under the supervision of Professor Chiranjeev Bhattacharya. We request the audience to keep your microphones on silent for the duration of the talk, except while asking questions. Questions can either be asked anytime during the talk or by unmuting or speaking directly or typing them in the chat box. They will be relayed to the speaker. Over to you, Professor.
Hello and good evening, everyone. Can you all see the slides?
Yes, Professor.
Oh, yeah. Great. Yeah. Welcome, everyone, to my talk on feature learning in deep networks. This is more of a conceptual talk rather than an application or a theory talk, right? So there will be theoretical concepts introduced, but it's more of a conceptual narrative rather than theory, right? So it's plausible that some of the things that I'm talking about is not exactly within in your knowledge right now, because I might be alluding to some advanced theoretical concepts, but it doesn't really matter that much, because this talk really does not really require too much background other than a basic background in machine learning and a basic deep learning background. So is that a fair assumption? So how many of you have no idea of deep learning or machine learning? So if there are folks here who have no idea of ML or DL, they will find it hard to follow. But if you have any, what happened? So if you have any background in machine learning and deep learning, you will be able to follow at least most of the talk. But feel free to stop and ask me for questions anytime in the middle of it. Right. So I'm very happy to talk about our work on feature learning in deep networks. This is joint work with several of my students and Professor Chandrasekhar, also from IIT Madras. Okay. So we will be working in the classic supervised learning setup. Okay. So we'll have a standard x, y tuples of data, and our goal is to learn a model which is a function from your instance space to the output space. Well, the learning algorithm is something which just converts the training data into a model, and we will use the word feature quite a bit, and it's abstractly taken to be some function from the input space to reals. So this is about all the background that you need to follow most of the symbols in the talk. The core question that motivates our work here is, why do neural nets work? Right? So it's now, I'll take it for granted that neural networks work well, right? Because that's kind of the huge reason behind the AI boom, and it's been the case for at least 10 to 15 years now. But why should they work? So typical neural networks have something like 10 to 100 times more parameters than data. Why should they work? Right? So there is so many ways in which they can fail, but they still succeed. Right? There are so many questions. Right? So why do they not overfit? What structure of the data is really discovered by them? And more practically, you can ask the question: okay, is that it? Right? So have we already hit the holy grail of machine learning, and is there nothing further than there is no frontier further to explore, right? So do faster, better, more reliable, or more interpretable learning algorithms exist, or is that it, right? So have you already hit the maximum possibility? And more fundamentally, the word deep learning already implies that there is notion of layers and depth implicit in the architecture and the models. And that's indeed the case for pretty much all the state-of-the-art models that are used. Right? So everything from your chat GPT to your CNNs for classifying images to all your models for transcribing speech, all of them have a notion of layers. Right? Why exactly is it required? Right? So of course, the immediate answer is that they work, right? So the shallow models where you just process input directly into the output were pretty much the norm until, let's say, 15, 20 years ago. And about 15 years or so ago is when the notion, having layers, right? So multiple steps of processing, all of which are learned together, became the succeeding framework paradigm, right? So why is that required? The empirical answer is that it's because they work, right? They work way better than shallow methods. But why, right? So it's unsatisfactory to theory researchers, right? So it seems unexplained, right? So it's I give an analogy, which is we are in the era of steam engines before thermodynamics. Right? So if you look at the chronology of when steam engines were invented, it was around the 1600s. But thermodynamics really came into play only in the 1700s. Right? So there was about a 100-year period where people were using steam engines to transport troops and cargo across the country. But really, no one had a fundamental idea of why steam engines had to work. Hello?
Yes, Professor, you're audible.
So the power just went off here. So I was just wondering if the UPS is working. Yes.
Okay. Okay.
All right. Right. So let's go back to the presentation. Right. Yes. So the reason why theory researchers are unsatisfied is it's the kind of similar reason would let's say Lord Kelvin would be unsatisfied with steam engine working. Right. So it's the steam engines work. Right. So it's an undeniable truth that steam engines work, but it does not. You don't have answer to questions like, okay, is this the maximum that you can do? Right. So is it, given this, I have 1 ton of coal. Is this the best way to transport, let's say, this train from one end of England to another end of England? Right? So, what are the limits to, let's say, this energy, and what's the? I mean, potentially, can you answer this question? Right? So, if we dump enough coal into the steam engine, can it go to the moon? Right? This is obviously impossible. We know it's impossible. We know that from law of conservation of energy and all that. We know that the energy required to go to the moon would, by a single, let's say, steam engine would require probably 1 million tons of coal, and we don't really have that. But you could not have answered this question in a concrete negative, let's say in 1600. Right? So maybe it's a very plausible thing that if you dump enough coal into the steam engine, maybe the locomotive would go to the moon. Right? We don't really have that impossibility statements right now. Right? So we really need to do this billion computations to classify an image as a cat or a dog. So there are a lot of fundamental questions that remain unanswered. So that's why theory folks are unsatisfied with the current state of affairs. So there are multiple schools of thought on why deep networks work. Right? So the first school of thought is simply the kernel school of thought, which is just that neural networks are simply efficient implementations of kernel methods. Right? So this school of thought is really headed by what's called the neural tangent kernel, which argues that your model is just a linearization around the initial parameters. Right? So this Taylor's expansion of the model around an initial parameter theta, where you say that y hat of x theta is simply y hat of x theta naught plus theta minus theta naught times the gradient of with respect to theta of the model. Right? So this is a standard Taylor series first order approximation, and this gives you all that you need to know to explain your kernel methods, right? So that's the kernel school of thought, which says that neural networks are simply efficient implementations of kernel methods. It's a very elegant school of thought, and there is a lot of theory that's built around this particular school of thought. There are, however, a few niggles, right? So the first thing being that deep networks with infinite width, which are mathematically equivalent to the kernel methods, they perform worse than finite width neural networks. Right? So if you argue that something finite is an approximation to an infinite width thing, the finite width thing should actually perform worse, right? But it's the other way around. The finite width nets really outperform the infinite width networks, right? And secondly, there is also a technical reason that the neural tangent kernel is not constant during training, right? So these two niggles really prevent us from saying that that's it, right? So neural networks are simply kernel machines. So that's not the full story. That may be a major part of the story. That's not the story that makes neural networks outperform linear methods and kernel methods. So then there is the feature learning school of thought, which says that the neural network learns apt features for the data in the training phase, right? So this entire sentence requires a decoding, right? Which is, what do you mean by apt? What do I mean by features? What do I mean by apt features for the data, right? So this entire thing is vague, but that's really the core idea behind the feature learning school of thought, which argues that it's not equivalent to your deep networks learning is not exactly equivalent to a kernel machine, right? So there are a lot of representation theory arguments, right? So which argues that your number of linear regions in the model is exponential in depth, right? And they also, that you can easily prove that representing some deep networks with shallow networks requires exponentially more parameters, right? These are representation theory arguments which are useful to an extent, but it does not explain how your learning process discovers those parameters, which is really the core question of learning dynamics and understanding why deep networks, or rather, why does gradient descent discover the right parameters. Right, so here's an outline of the rest of the talk. Firstly, I'll explain, or at least try to explain, what are features. Right? So the word features is something which you will see peppered throughout the talk, but what does it even mean, right? So I here will try to make a distinction between two types of features. One is a data feature and a model feature. So data features are a property that is intrinsic to the data, right? So you have that feature regardless of whether you are using an ML model or not, right? So let's say you have images and you are trying to, let's say, distinguish between cats and dogs, right? So whether there is a pointy ear or not is a property of the data. It's not really a property of the model, right? So whether an image has pointy ears or not is a property intrinsic to the data, and regardless of whether you have an ML model trained on it or not, it exists, right? So that's an example of a data feature. And then you have model features, which are really a property of the model, right? So it potentially can represent data features too if the model is trained on the data, but model features are a property of the model, right? So I can potentially have a model which is just set to initialization, and that still has model features. Right? So often there is no correct answer to the question, what are model and data features? But there are multiple potential answers, and I'll try to go over some of them. Right? So the classic example for data features is just raw data. Right? Let's say you are trying to detect heart risk from your sugar, cholesterol, your pulse, and your blood pressure. These numbers, this sugar, cholesterol, pulse, blood pressure, those are the data features, and you could argue that they are the data features. That's a very valid notion of features. Then you have things like you have let's say data, scattered plot of data like this, in which case you can argue that the dimensions along which there is large variance, those correspond to data features, right? So in this example, the diagonal arrow here corresponds to a large variance direction, and that's one data feature, whereas the species second dimension corresponds to a direction which has lesser variance, and that might not be a good data feature, right? So that's another notion of data features. Another particularly interesting thing is to argue that only features that are informative with respect to the label, that's our goal, right? So our goal here is simply, let's say, classification, let's say simply binary classification. We are only really interested in features that are useful for us to classify. Right? In that case, only features that somehow contain the information about the label are useful features. Right? For example, in this case, in this example here, having information about square root of x1 squared plus x2 squared is really useful, right? So that's the data, that's the part of the data that gives you information about the label. Right? So we'll argue that only functions of the data that contain information about the label are useful data features. all three of these notions are perfectly valid notions. Right? Now we'll go to model features. Right? Let's say you have a model like this. Let's say your y hat of x is just say W transpose x. Again, the model features, it's the most natural notion of model features is just x, right? So this corresponds to the data feature notion where your raw data just happens to be the data features. Right? So in the case of a linear model, the most natural notion of model features is also just the raw data x. Right? But then you could have something like trees, right? Let's say you have a tree model like this, right? So where the root node just says is x1 plus x2 is greater than or equal to 1. If yes, it goes left. If no, it goes right, and so on. For this model, you could argue that the model features are simply the internal nodes of the tree. Right? So x1 plus 2x2 is an important feature. x3 minus x4 is an important feature. 2x7 plus x9 is an important feature for the model. Right? So these are model features. This is a natural notion of model features that you can apply if your model happens to be a tree. Right? Then you might have more complex models like CNNs and so on. Right? So in which case, a natural notion of model features might be each channel of your or each channel of each layer happens to be model feature. Right? So that could be one notion of model feature. If you have a kernel model, a natural notion of the model feature is just the feature function p. Right? So if you have a kernel k, which implicitly represents inner product between phi of x and phi of x dash, then your natural notion of feature is just phi. Right? This is really just a linear model with the feature being phi. Right? All of these are valid notions of model features. Right? Okay, fine. But what is feature learning? Right? So now we have a data features and model features, but what is feature learning? So here is at least my attempt to define feature learning, which is your model features change during training to better align with data features. Right? So if this happens, then I'll call feature learning as happening. Otherwise, feature learning does not happen. Which means all of your linear and kernel models, where as you train, as your parameter changes, the features don't change. Right? So take both model feature 4, which is kernelized models, where your natural feature is just phi, or for example, let's say the linear model where the model feature is always x. Right? So it doesn't matter what your parameters are, the model features remain the same. Right? So in this case, by definition, your model features are not changing. Right? So because your model features are not changing, feature learning cannot happen. So that's the definition of it. So in that case, given that we know that linear models and maybe kernel models are sufficient for a lot of problems, is that even needed? Right? So is feature learning absolutely essential? The answer to that is no. Right? So you can absolutely do well without feature learning. Right? So for example, in low dimensional data like this, right? So here is my take on when you need feature learning. Right? So if you have a data where, let's say, k nearest neighbors works well, then you don't need feature learning. Right? So it's a baseline model which everyone understands, which is k nearest neighbors. And if k nearest neighbors already works well, you don't really need feature learning for that to perform well on that data. Feature learning is absolutely not absolutely essential, but the moment you have high dimensional problems, if you don't have feature learning, you are always leaving some performance on the table. Right? So you are not extracting the full value of your model if you don't do feature learning. Right? So that's the reason why deep networks outperform on high dimensional data like images, text, and so on. But they don't really outperform on classic feature vector data. On classic feature vector data, you still find kernel methods and tree methods are still very competitive. Right? You can train deep networks to do well, but you have to do a lot more to make them comparable to, let's say, classic tree methods like XGBoost and so on. Right. So what's the current theory on feature learning? Right. So let's take the simplest, or rather the only kind of feature learning theory that's available now, which has to do with learning single layer neural networks. Right. So where, let's say, your true label happens to be of the form like this. Right. So your y star of x is your true label, happens to be of the form some unknown function, unknown scalar function u of some unknown w star dot x. Right. So that's your true label. Right? This is called a single index model, where your true label function is really just a scalar function of another scalar function, right? So that's the W star is, you don't know W star as well as you, right? So you say that your labels are given by U of W star dot X for some unknown W star and some unknown. So U, however, is a scalar function which just maps reals to reals. That's your this kind of model. And if you, let's say, you try to learn a single layer neural network, right? So which is given by the neural model here, your y hat of x is, let's say, just sum over a weighted sum of sigmoids of wi dot x, where wi is the parameters, right? Here, this is pretty much the only kind of feature learning result you will see in current literature, which is still highly non-trivial. Because even this problem, right, is not trivial, because in high dimensions, this you can still fail, right? So if you try to learn your this kind of Y star with your, let's say, classic linear models or tree models or any shallow methods, they can fail miserably simply because of the curse of dimensionality, right? So your W star is a high dimensional vector, and you have to learn that, right? And if it can, you can easily show that classic shallow methods can fail miserably. But neural networks do well on this kind of problems under certain conditions, right? So here is an illustration of what happens. Let's say here is this figure shows a generalization where your W star is not a, you might have multiple W stars. So that's given by these black dashed lines, and your WIs are your initial, let's say, your black dots here correspond to the initial WIs, and your these curved lines show the trajectory of your parameters WIs as the training goes from initialization to the final thing. Right? So you can clearly see that the black dots from initialization go to the yellow dots at the end of training, and they all align with one of the W star vectors. That's at least it's not particularly surprising, but you can easily show that if you train standard shallow models, they can easily fail. Right? So which is here is the deep networks really do succeed in this particular setting. I can theoretically show that these WIs approach W star. Right? As you train from random initialization, these WIs will approach W star. So this is pretty much the only kind of feature learning theory result that you will see in current literature. Okay, fine. But is that sufficient, right? So here I make a case that we need a better feature learning theory. Right? Firstly, the problem setups are not challenging enough that you can say that, for example, let's take this problem setup, right? So your Y star of x is U of W star dot x. This problem setup is just not challenging enough that deep networks are the only way to go, right? So there are single index model methods. If you knew that your Y star of x has this structure, you would use those methods. Right? So you would use single index model learners, which can perform well on this type of data. So deep networks are not the natural options here for this kind of problem. Right? So that's the first point. And the second and more important point is that there is the need for multiple layers is still completely unexplained. Right? So here you can see the neural model is just a single hidden layer neural model. Right? So you have a hidden layer, but it's just a single hidden layer. If it does not explain why you might need multiple layers for performing well. Right? That's simply because this data setup is not challenging enough. And if you look at real data setups, you will see this multi-phase learning dynamics. Right? So you have a phase 1, phase 2, phase 3 kind of thing that you will see in empirical performance, and that's just not present here at all. So all of these make this an unsatisfactory feature learning theory situation right now. So to that end, we at least take a direction where we propose a new feature learning hypothesis and a mechanism of feature learning. Right? So that's the main. These two slides are the main setups for why we do the work that we do. Right? So the first thing is that we say that data features. Our notion of data features are simply surfaces in input space that are regions of discontinuity. Right? And similarly, model features are also surfaces in the input space that are regions of discontinuity in the model function. Right? So the difference between data features and model features simply becomes the difference between a label function and the model function. So, and we say that the feature learning happens when your family of discontinuous surfaces expressible by the model are a right fit for the data features. Right? So don't worry if you don't fully understand what's going on here. I will try to explain this with more firm examples later on. Right? And okay, what's the mechanism for multi-layer learning? That's the main reason why we were unsatisfied with this with the current state of the art for feature learning theory. Right? So the mechanism is the main reason why we do the work that we do. Here, our at least our proposal for why multi-layer learning works is just that layers act as lenses for other layers. Right? So that's perhaps a one sentence summary of our work, which is the neurons here play dual roles, right? So which is they play a role of separator for data lensed by other layers, and they also play a role of component of a lens for other layers, right? So this dual role sets up a positive feedback loop, right? So this is the crux, or rather a one sentence summary of the mechanism of multi-layer learning. Actually, this is our proposed explanation, right? So this is it's a bit grand in its scope because it's trying to explain all of deep networks, but unfortunately, the very concrete nature of the result here indicates that you have to make some assumptions on both your data as well as your model for you to actually even verify these statements. I think, yeah, so that's what I'll do next, right? So I'll set up the data, right? So the data conditions under which we actually try to demonstrate the mechanism as well as the hypothesis, and the model. So the data setup we are going to be using is oblique decision trees, and the model setup that we'll be using is architecture known as deep linearly gated networks. Before we go there, I think this is a good place to stop for questions, right? So any questions from the audience?
Professor,
Yes.
a small question. You
Yeah.
are mentioning it as while mentioning feature learning, you were explaining it as each layer works as a lens. But
Yes.
somewhere, can you explain more about it? What do you mean by the lens? I mean, acting as lens and stuff.
Right. Yes. I'll try to do that. So yeah. So that's what the rest of the talk is. I'll be doing that.
Oh,
Right. Great. So yeah, now I'll try to explain the data setup. Right? Our data setup is simply oblique decision trees, right? So which is for the rest of, I mean, or rather for the rest of the talk, we'll just be working with simple binary classification, right? So our goal is to just do binary classification. That's it, right? So it's nothing complicated. No images, no let's say multi-class, no speech to text, nothing complicated. Just plain and simple binary classification. So we assume that the true labeling function is an oblique decision tree. What do I mean by that? That is, we assume that there exists a tree like here, right? So where your label is decided by just following the path of the tree and giving the label corresponding to the leaf node, right? So for example, in this particular decision tree would say that, let's say you have a 10-dimensional data, the root node would just check x1 plus 2, x2. If it is greater than or equal to 1, if it goes left. And x3 minus, it checks for x3 minus x4. If it is greater than or equal to minus 1, it goes left and says that the label for this particular data point x is plus 1. Otherwise, I mean, based on whatever leaf node it ends up on, that's the class label for that particular instance. Of course, we are for training the model, we don't have access to this, right? So that's not, if we have access to this, then there is nothing to learn here, right? This is a synthetic data setting where we assume that the data is at least the labels for the data is generated by a hidden decision tree. So why am I calling it oblique decision tree? Standard decision trees don't have multiple attributes in a same node, right? So a standard decision tree would something like be like x5 greater than or equal to 3 and is x7 less than or equal to minus 2, right? Those kind of questions are the only kind of questions that are allowed in a standard decision tree. In an oblique decision tree, the decisions are made not based on single attributes, but rather linear combinations of attributes. So that's the difference between an oblique decision tree and a standard decision tree. An oblique decision tree is a generalization of a decision tree. So that's the setup. So this setup is simple enough to explain while being complicated enough to pretty much befuddle all machine learning models out there. So here is an example of how decision tree might, oblique decision tree might look like. Here, let's say we consider this depth 3 decision tree. So we'll always have complete decision trees, so complete binary trees. So here's a because step 3 you have 15 nodes with 7 internal nodes and 8 leaf nodes, right? So each leaf node corresponds to either, let's say, +1 or -1, right? So, and each internal node corresponds to a hyperplane, right? So you can see this particular figure here. The root node corresponds to this hyperplane. I think it's better to use the mouse here. I'm using the mouse here to point. So can you see my cursor?
Yes, Professor.
Okay, great. So the root node here corresponds to this particular hyperplane, and which is 0, and the node 1 corresponds to this hyperplane, right? So you can see that only the root node hyperplane has extent through the entire domain, right? So every other hyperplane has limited scope, right? So for example, the hyperplane corresponding to node 1 only goes from here to here. It ends here. It doesn't, even though technically the hyperplane goes even further south here, it just stops. It doesn't matter what the hyperplane here in this region is. Only this region matters, right? And based on whether, let's say, 7, 8, 9, 10, 11, 12, 13, 14 are leaf nodes, which are either +1 or -1, and let's say data falling in 7 happens to be, let's say, +1, and +1s are all shaded red, right? And the negatives are all shaded, let's say, green, right? So that's what this particular figure corresponds to. So you can see that if you had a scatter plot and shaded the data based on, or colored the data point based on the label of the thing, this is how your scatter plot of the data would look like, right? So you might have reds corresponding to positive labels and greens correspond to negative labels, and this is how your data would look like. Great. Okay. So, okay, now, unfortunately, but once the data is generated, the model really does not see these lines. It only sees something like the figure on the right, right? So even if you have infinite data, you don't really see the lines, right? So on the left, you only see the data, which is the scatter plot might look like the thing on the right. The lines are not exactly presented to you immediately, right? So what you see is only the data. Okay? Of course, for 2D, you can do a scatter plot and draw a line, but you can't really do that for, let's say, 100-dimensional data. You can't really draw the lines in 100-dimensional data. In such a situation, how do you characterize the hyperplanes of the ODT? Like the ODT features here can be essentially viewed as hyperplanes of maximal discontinuity. What do I mean by that? Let's say you had the data on the right, right? And if you could draw any hyperplane or any line here, only the lines that align with one of the ODT hyperplanes would correspond to discontinuities. Right? Any other line, so let's say you draw a line which is not one of these lines. Right? Let's say you consider you draw a line like this. I'm saying it's not a discontinuity. What do I mean by that? It is if you take a point infinitesimally close to one side of the line and you move from that side to the other side, the label is not likely to change. Right? So yes, there could be changes, but it's not going to be the label is not going to change for a vast majority of the points. Right? Maybe you consider the horizontal line like this. Right? The horizontal line here through the middle is clearly not one of these ODT lines. Right? If you move from just below the line to just above the line, for most points, the label will be both red or green. Right? There are a small fraction where it goes from green red or red green, but that's with zero probability, right? So if you pick a randomly chosen point with probability 1, you will find that if you move just below the line to just above the line, the labels will stay the same. Right? So that's not a discontinuity. Right? But if you chose a line corresponding to one of the ODT nodes, they would actually be discontinued. Let's say, for example, if you pick this particular line, right? So anytime you pick a point like this and you move to the other side of the line, you're going to have a red-green discontinuity. Right? So the only lines where there's a discontinuity are going to be the ODT hyperplanes. Right? So the ODT features can essentially be viewed as hyperplanes of discontinuity. Okay, great. So why are we bothered about learning ODTs? Learning a model to fit data labeled by an ODT is a truly challenging problem. Right? Why is that? Because all standard shallow learning approaches fail miserably due to the curse of dimensionality. Right? So this is something which only if you try and fail you will learn. Which is if you try to fit, let's say, a k nearest neighbors or a kernel method, you will find that it just does not work, right? So if you have high dimensional data labeled by an ODT, you will be hard pressed to beat something like 60-70% accuracy. However, if you train a deep network, let's say a ReLU network or some other network, they do perform well. Right? So deep models are truly required to fit, and they do perform well. Okay, so that's the data set. Okay, and then what model are we using? We could technically just use a standard ReLU network, but it has issues, right? So main reason being that we can't really characterize what do we mean by a model feature for a ReLU network. Right? It's hard to characterize the set of model features for a ReLU network, and that's the reason why we make this alternate architecture, which is motivated from a ReLU network, but not really a ReLU network, which we call the deep linearly gated network. So what is a deep linearly gated network? It has a similar structure to a ReLU network, where it has multiple hidden layers, and each hidden layer has a bunch of neurons. It however has two networks, right? So it has a gating network and a value network, right? So the details are not important. The only it's just motivated from a ReLU network, and you can do a forward pass and a backward pass and update the parameters of the network quite efficiently, right? So that's all that you need to know for this particular step for the deep linearly gated network. To just convince you that this is a valid architecture, we can easily just run this algorithm, run the model for several standard data sets, and it is competitive. It doesn't beat the state of the art, but it is competitive, just to show that it's not a silly architecture which has no use. But that's not the reason we are proposing this architecture. The reason we are proposing this architecture is so that we can study the mechanism of feature learning, and not really replace the standard deep network. The main reason we do that is you can express the model output of a DLGN in an equivalent way as a sum of paths, right? So that's the alternate expression here. You can see that the model output of a DLGN can be expressed as sum over the paths g pi f pi, right? So pi is a path, and what do you mean by a path? Let's say you have L hidden layers, and each hidden layer, let's say, has M hidden nodes. You can pick one of the hidden nodes in each layer. So it means there are M power L ways in which you can pick a path. Like, for example, you can pick, let's say, node 1 in layer 1, node 2 in layer 2, node 3 in layer 3, and node 1 in layer 4, and so on, right? So each time, for each layer, you can pick one of the M nodes. So you have L choices to make. So it's M power L possible paths here. Right? So that's your path pi. So you can sum over all the M power L paths. G pi is just a scalar which we can parameterize, and the key thing here is to observe f pi. Right? So f pi of x is the is given by the gating function, which you can see is, you can ignore the g pi for now, right? So g pi is just parameterizing the weights for every path. F pi, on the other hand, it's expressed as a product over the L layers. Right? So if we approximate a sigmoid by a step function, each product is a step function with a half space, right? Which means that everything on one side of the half space you get a 1, everything on the other side you get a 0, right? So the product of such things corresponds to really the intersection of half spaces. So which means that f pi of x really corresponds to an indicator function for a convex set given by the intersection of the half spaces, and 0 outside that particular convex set. The key, this is a pretty simple expression. The key power of the model comes from the fact that it's a sum of M power L such paths, right? So that's where the power comes from, because M power L can easily be quite large. Right? So even if you have, let's say, 10 layers with 20 neurons per layer, which is a reasonable, which would not be considered a large network. You have 20 power 10 possible paths, right? So it's a sum of 20 power 10 terms. Of course, this is just an equivalent representation, right? So you will never really do this computation explicitly, right? So you will do the computation implicitly through the forward pass, which we explained here, which we didn't really explain here. But you can equivalently break down the output this way. And how does this help us? This helps us because the model output is explicitly expressed as a sum of product. Okay? Because it's a sum of products, you can actually analyze the internals of the network. Right? So as opposed to a ReLU network, you cannot really express a ReLU network as a sum of product of simple things. Right? So here, the DLGN is simply can very easily be expressed as a sum of product of simple half space terms. Right? That's the main power of the DLGN architecture, which means that it's intrinsically interpretable, right? As opposed to a ReLU network, which is not intrinsically interpretable. So here's an example. Let's say you take this simple example where you have two hidden layers with two neurons each, right? So that means you have 2 power 2 possible paths, right? So take this example here. You have the orange-green path, the orange-purple path, the blue-green path, and the blue-purple path. Right? So you have 4 paths. Right? Each path, let's say you take the orange-green path, right? So the orange-green path, the gating function f pi really corresponds to the product of the half space for the orange and the product of the half space for the green, which is given by this figure here. And the orange-purple path is given by the product of the half space given by the orange half space here and the purple half space here. The product becomes an intersection. Right? So this, so you have a path which has a value of g pi inside this particular region and 0 outside it. And the g pi is just a scalar which says what's the value inside a particular path. Right? So you can ignore that for now. The main, the interesting feature is the gating function given by the f pi. Right? It's a product of half spaces and which is easily interpretable. Right? So because even though there are m power l paths, there are only m into l half spaces. That's the here. Yeah, in 2 power 2, you don't see the difference. If you have, let's say, 10 layers with 20 neurons each, there are 20 power 10 paths. But there are only 20 into 10 half spaces. Right? So that's analyzable. 20 200 half spaces is tractable. 20 power 10 paths is not really tractable. You can't really analyze all 20 power 10 paths, but 200 half spaces is well within reach of tractability. So the DLGNs are a linear combination of path gating functions, and each path gating function is a product of neuron gating functions, and each neuron gating function is just a half space. It's an indicator function of a half space, which means that the neuron gating functions are a natural notion of a model feature for DLGNs. Right? And unlike ReLU networks, where so you can make something similar for ReLU networks, but if you do that, it's not a product of half spaces. It's a way more complicated thing. And because it's not a product of half spaces, the path features don't really make sense. They are powerful, but you can't really make sense of the path features. Unlike here, where each path feature is simply a product of half spaces. So right. So now we can ask the question: okay, how does feature discovery happen in DLGNs? So here's an example of how it might happen. Let's say you train your DLGN on the data on the top. So when you initialize, your DLGN hyperplanes are close to random. That's given by the bottom left here. By the end of training, however, the hyperplanes of the DLGN align with the hyperplanes of the decision tree. And that's given by the red lines here, aligning with the black lines of the decision tree. And you can see that the root node, which is the node 0 here, has more hyperplanes close to it than the other. This is intentional, right? So this is the notion of hierarchy that we actually see for this particular setup. So here's a more quantitative example where you train a DLGN with a 15 node, or rather depth 4 ODT data, and you find that out of the 400 hyperplanes, there are a vast majority of them actually end up being quite close to the hyperplane corresponding to the root node. Right? But pretty much all the hyperplanes of the ODTs are discovered. Right? So this is the feature discovery or the feature learning phase of the learning process. Right? So how does gradient descent help in actually discovering the features of the model, right? Or the features of the data? Right? So that's the core question we want to answer, and at least we can characterize the feature learning happening as the model features approach the data features. Right? So this is a meaningful statement to say for this particular data setup. Right? So you can't really say the statement for, let's say, you train a ReLU network, or let's say you train a ReLU network on ImageNet data. This statement even does not make sense, right? So the model features approach data features. What do we mean by that? How do we even measure this approaching? Right? How do we measure the fact that the model features are approaching data features? You can't even measure this statement because it's vacuous. Because we have made everything concrete, right? So the model features, data features, everything is concrete. You can actually measure how the model features approach data features. So that's the story here. Right, so that's the DLGN feature learning conjecture. Okay. However, what is the mechanism by which this happens? And so that's really the core reason we even started doing this. And to do that, let's actually dig a bit deeper. Right. So this particular figure only tells you the result at the end of training. What happens during training? Let's take a simple setup. Right. So you are training a depth 5 decision. Let's say your label function is a depth 5 decision tree, and you are training a model with let's say a 5 hidden layer DLGN with 16 nodes per layer. Right. Let's consider each neuron as a point. Right. So that means you have 5 into 16 is 18 neurons. We can, even though I call it as indicator functions, that's really a sigmoid. Right. So because it's a sigmoid, you can actually measure the norm of the gating weights. So at initialization, it's pretty random, right? So it's the gating neuron norms are between 0.5 to 0.6, and the cosine similarity of the gating vectors with the ODT hyperplanes it's pretty random. There is no pattern to discern here at initialization. However, even immediately after one epoch, you see a pattern. Right? So what do the colors here mean? The colors mean that the color is purple. It means that the nearest ODT hyperplane for a given DLGN feature is a level 0 node. Right? So if the color is blue, it means that level 1 node, and so on. Right? There is only one level 0 node, which is the root node, and there are 2 level 1 nodes, which is the children. There are 4 level 2 nodes, 8 level 3 nodes, and 16 level 4 nodes. Right? So that's how a decision tree works. At initialization, there is no pattern, right? But immediately, even after the first epoch, you see something strange happen, right? So which is that pretty much all the DLGN hyperplanes or DLGN gating neurons get closer to a level 4 ODT node, which corresponds to the leaf nodes. That happens at epoch 1. It still does not align completely. Right? So you can see the cosine similarity is still only between 0.2 to 0.5. Right? So only when the cosine similarity is 1, we can say that our ODT hyperplane has been discovered. Right? Until then, it has not really been discovered. Right? So it's on the way to discovery. Right? That's the status. Right? At epoch 2, something immediately different happens. Right? So you can see the purple preponderance here. Right? Purple corresponds to level 0, which is the root node. Right? So immediately after, at the beginning of training, the leaf nodes get a signal, but after that the root node takes over. Right? So that's the story. But at this stage, you still don't have the cosine similarity has not hit the levels of 0.9 or 1 and so on. Right? So it's still in the range of 0.2 to 0.8. Right? But as the training progresses, you see that the cosine similarity hits 1. Right? You can see that the first DLGN hyperplane or DLGN gating neuron that actually hits cosine similarity of 1 is purple, which corresponds to the root node. At the end of training, however, you can see that all the DLGN gating norms which have a norm greater than a threshold have cosine similarity of 1 with respect to one of the ODT hyperplanes, right? Which means that all the all the confidently discovered features correspond to data features. So it's all the confidently discovered model features correspond to data features, or rather interesting or relevant data features. That's the story here. Okay, but why does that happen? So the dynamics reveal interesting hierarchical behavior. That is, the hyperplanes are learned in the increasing order of distance to the root of the OT, right? So which is the first discovered feature happens to be the root, then the children, then the children's children, and so on. Right? So that's the approximate hierarchy that is visible in the training dynamics. But why does that happen? Right? So how can we explain this? We can actually simplify this model even further to do a single path DLGN, right? So which is, you have, forget the m power L paths, right? So which is, you have L layers and m neurons per layer. Let's just have L layers with a single neuron per layer. Right? So just a single path actually exists. Right? Even in this, you see interesting behavior. Right? So for this, we can actually derive the gradients, right? And the gradient of the model output with respect to the parameters, let's say W1, one of the layer neurons, really splits into three components. Right? The three components which we call the residue, the lens, and the blinder. Right? So you can see that we are trying to get the gradient of the loss with respect to one of the parameters W1, and the other parameters W2, W3, W4, all the way to WL enter the gradient expression through the lens. Right? So that is, when you want to update W1, the other layer parameters essentially play a role of lensing the gradient, right? So only when you have excess where these are all high, your gradient, they contribute to the gradient, right? So the other parameters W2 to WL form a role of lens, right? So this W1, however, is arbitrary, right? So I'm just pick W1 for the sake of convenience. You could have picked anything, right? So which means that the W1 plays two roles. The first role is it by itself tries to update to minimize the loss that it sees, but it also plays a lens for as a component of a lens for other layers, right? So that's the two roles that I mentioned. Right? Every weight vector Wi tries to be a separator, but it also is also a component of the lens for other layers. Right? So this two roles simultaneously really starts the positive feedback loop. So that's the main crux of our theory here. So that goes into the details, which I can't really go due to the lack of time, but the crux of the story is just this. So with that, I think I can come back to the story here, which is, there was a couple of questions here, right? So what do I mean by lens? That was the question, right? So the dual roles here, right? So each Wi plays two roles: the separator for data lens by other layers, and it's also a component of lens for the other layers. And these two roles are essentially evident in this gradient expression, which we saw here. Right? That's what I mean by lens and separator. I know that this is a lot of this requires more details, but the the high level outline is just really simple. That's all for the story here. Any questions from the audience?
Professor, a small question here. I think you assume the loss function to be this cross entropy loss, right? Here,
Yes, yes,
I suppose that is because of smoothness, or
yes.
is there and have you tried on different loss functions as well here? Or
So the problem that we are attacking is classification, and for classification, really cross entropy loss is the standard loss to use. If we tried for other losses, so this story makes sense even for other losses, but then the problem, the data setup would not make sense. The data setup is for trees and discrete class labels, for which the cross entropy loss is is the loss that makes sense.
okay.
Yeah. But I mean, you could technically apply the gradient analysis even for even for, let's say, the squared laws or some other laws, right? So you could absolutely apply the gradient analysis for that, but the data setup would have to change.
Oh. Professor, it seems like there is one more question from online.
Yes. Yes.
Can I read it for you?
Yes.
Sir, can we also get some impossibility results based on this analysis?
Yeah. Right. So, good question, Piyush. So, which is the answer is not really, right? So, because that's not really the goal of this particular setup, right? So, which is the standard impossibility results you would get, right? So, which is just based on curse of dimensionality, right? So, which is because this particular problem is really just a sub problem for of let's say. So let's go back to the tree. Right? So, or rather, I think I have a better figure. Right? So let's say this is the tree from which the data is labeled. Right? You can see that even though you might have, let's say, you have 100-dimensional data, right? But really the data labels only depend on u0.x, u1.x, u2.x, all the way to u14.x. Even if your x is 100-dimensional data, the labels really depend only on these 14 or rather 15 projections. It's a pretty complex function of those 15 projections, but it's really a function of only those 15 projections. And just by virtue of this, you have impossibility results, right? So, which is that your label depends only on a small projection of high dimensional data, right? So, which is your this alone enables impossibility results, but only for linear methods, right? So only for linear or kernel methods you can easily build impossibility results, because when you are from a random initialization, if you pick, let's say, some w, it's extremely likely that that w will be orthogonal to all the ui's, right? So it will be orthogonal to u0, u1, u2, all the way to u14. Right? If that happens, the w gets no signal, right? So it gets no signal and it will not move at all, right? So of course there are some wiggle rooms here. It's not be exactly orthogonal. It will be orthogonal up to some 1 by root n factors, and you can control the variation. But the crux of the story is that there'll be very little signal for the w to move along any of the uis. But that's an impossible result for shallow methods. You can't really get an impossible result for deep methods which have interaction between the features. And that's in fact the reason why why I say that lens is important, right? So let's go back to this figure, or rather, let's go back to this figure. So here, from the context, if you had the entire data at your disposal, let's take simply your x is zero mean Gaussian, right? Let's say a standard Gaussian, let's say 100-dimensional covariance is identity. X is standard Gaussian. U0 is a high value feature, right? So because only if you know U0, or rather only if you know U0.x, you can actually make good predictions. But from a global sense, U0.x is totally useless, right? So look at it from, let's say you're trying to build a tree using greedy methods. Right? U0 is a totally useless feature, because there's both on the left side of U0.x equal to 0 and the right side of U0.x equal to 0, the data is perfectly balanced. So you will never pick u0.x. So your update will never be u0.x. It will be one of the leaf nodes, in fact. And that's really the failure point. But let's say somehow you are already looking at the set of data points restricted by, let's say, u10.x greater than 0, u4.x greater than equal to 0, and u1.x greater than equal to 0. For the data that is lensed by these particular half spaces, u0.x is high value feature, right? So u0.x makes it linearly separable. So there will be a high gradient signal along u0, and your parameters will move along u0. So it's the lenses that enable your parameters to move along these features. Right? If you didn't have the lenses, right? So if all of the data or all of the parameters looked at all of the data, your parameters will not move along the interesting directions. Right? But because the parameters are not looking at all the data, right? That's the role of the lens. You are quite likely to move along a direction which has signal when compared to the original ODT. Right? So that's the reason why the process even works. Right? So that's not really an impossibility result. Right? So you can get impossibility results using classic methods in dimensionality. That is the dependence of your label is essentially in a low dimensional space, right? So even though you have 100 dimensional input, the label depends only on, say, 15 dimensions. It's 15 dimensional projection, and these kind of problems are intrinsically hard for shallow labels. They suffer from because of dimensionality, because the sample complexity grows exponentially in the ambient dimension 100 rather than exponentially in the real dimension of 15, right? So it's really depending on 15, right? So only it's 15 numbers, 15 dimensions that matter. The other 85 dimensions don't really matter here. But any shallow method cannot really distinguish between the 15 and the 85. They will treat everything equally, and you will suffer because of dimensionality. Yeah. Any
Also,
other?
a small doubt. Can we comment? So, based on our analogy here so far, can we comment something on the total number of layers that are required for good prediction?
That's a very good question. And for at least in this setup, it makes a lot of sense to set your number of layers of the DLGN to be equal to the depth of the decision tree. Right? It makes a whole lot of sense. Right? And why is that? Because if you have lesser number of layers, you just cannot, your model does not have the expressive power to express your decision tree. If you have more, it doesn't really help, but it doesn't hurt also, right? And that's visible in your empirical results. If you have, let's say, if your data is really labeled by a depth 4 decision tree, and you learn a DLGN model with, let's say, 4 layers, it performs the best, right? So with 3 layers, it performs worse depth. With 5 layers, the performance is moderately worse, right? So it's not significantly worse, right? So you're giving it more power, so that doesn't really hurt it, but setting the number of layers of the model to be equal to the number of the depth of the decision tree is what gives you the maximum performance. Of course, when you are training the model, you don't know that the depth of the decision tree, right? So if you knew that, it will obviously be so you don't know the decision tree, right? So you don't know the decision, you don't even know that the data is coming from decision tree. Right? So
Correct.
So saying that you have to set your model depth to be equal to the depth of the decision tree it's really only the creator of the data can actually do that, right? And because in this setting, I am the creator of the data, I know that you can set your model number of layers to be equal to the depth of the decision tree. And that's another reason, right? So because here you really need the model number of layers to be not just greater than 1, right? So if you look at classic deep learning theory results, though, you'll see that, okay, as long as you have a single hidden layer, all of your deep learning theory results will work.
Right.
Here, on the other hand, you actually need your number of layers in your deep model to actually match the complexity of the data. So that's another point of analysis that you can do.
Oh.
Yeah. Any other questions?
I think, Professor, you have answered almost all of our queries. And thank you very much for accepting our request and delivering such an informative talk. And thank you all audience for attending here and having a great time. So thank you all and have a great evening.
Yeah, thank you very much. Thank you very much.